let's start off this video with the challenge problem from the last video. So we have a car of mass m moving with a velocity v that locks its brakes and stops in a distance d. The coefficient between the tires and dry road is mu. And we want to know if the car was moving with a speed of 2v, what would its new stopping distance be in terms of d? Alright, well, we can use our relationship between work and energy. So we know work is force times distance, which equals a change in energy. The only energy we have here is kinetic energy, because we're going to set our gravitational potential energy to be 0 at the center of mass of the car, and there are no springs involved here. So the force that we're dealing with that causes this change in kinetic energy is the force of friction, and that is decreasing our kinetic energy, so it's a negative value. Force of friction will be mu times the normal force, mg, times our stopping distance, and our change in kinetic energy is our final kinetic energy 0 minus our initial of 1/2 mv squared. Alright, so we want to know what would happen if we doubled v. So our velocity is squared, so doubling v will increase it by a value of 4. So we'll have negative mu mgd. Well, you could say our negatives turn into positives, equals 4 times 1/2 mv squared. So this will give us 4 times the stopping distance, because a regular v gave us a stopping distance of d. So 4v will give us a stopping distance of 4d. Alright, now we want to know what would happen if we doubled m. Well, we can just use the same relationship. Work equals change in kinetic energy. We know our negatives cancel now, so mu mgd equals 1/2 mv squared. And you might have noticed from part A that our mass cancels, so we could quadruple m and we'll still have the same stopping distance d. Alright, for this first problem we have a small ball of mass m at the end of a string of length L, and that ball is released from rest from a horizontal position as shown. When the ball is at point P, we are given an angle theta that the string makes with the horizontal. So for part A, we just want to draw a free body diagram for the mass at point P. Alright, well, the force in contact will be our string. It makes a force of tension, and then we always have the earth that exerts a force on that ball equal to its weight, mg. In part B, we want to determine a formula for the speed of the ball at P. So we're going to use the conservation of energy to do that. And first we need to define our zero line where we have 0 gravitational potential energy. So I'm going to drop a string of length L. This is going to be the ball when it's at its lowest point. This is going to be our 0 gravitational potential energy. So the initial energy we have when the ball is at its highest point is only going to be gravitational. We have no springs, we have no elastic potential energy, and that's going to be equal to our gravitational potential energy at point P plus our kinetic energy. So at its highest point we have gravitational potential energy mgh. Our h is due to L. At point P, our height at P, we're going to be looking for this height. So we're going to take our L, and we're going to subtract this height. You might be able to see we have a triangle here. This is L. We can use our sine function, sine of alpha equal to our opposite of our hypotenuse. Call that x. So it's going to be x over L. You can see that x equals our L sine of alpha. And then we multiply that by mg. So we'll have mgl minus mgl sine theta, or I should say sine of alpha, plus our kinetic energy 1/2 vp squared. Alright, we can see our m's cancel, and you can subtract gl from both sides. So now we're left with that. We could say that gl sine of alpha equals 1/2 mv sub p squared. Well, actually, we don't have that m anymore. Alright, and then we can say Vp is going to be equal to 2 GL sine of alpha, and then the square root of that. So that is the answer for part B. Here's the second problem. I know it has a lot of words, but you can also look at the diagram, and a lot of times that'll really put some sense into the paragraph. But basically, we have a spring compress the distance x from the edge of a table. We have a mass. The mass is released follows a shown trajectory, and we have a list of given variables, and note that there is no spring constant. So first we want to know the time elapsed from when the block leaves the table to when it strikes the floor. Well, for this one, we can use projectile motion concepts. So let's look in the vertical direction. So we know we have an initial velocity of 0, because when the block falls off the table, it's initially moving horizontally. We don't know the final velocity. We know we have an acceleration of g, a change in y of h, and we're looking for our change in time. Hopefully you know the kinematic equation to use. Change in y equals initial velocity times time plus 1/2 gt squared. Alright, so our initial velocity is 0, so we can just solve for time. C equals the square root of 2 change in y over g. We'll just say downward is positive and to the right is positive. So that'll give us a time of the square root of 2h over g. Now for part B, we want to know the horizontal component of velocity just before the block strikes the floor. So in that case, we know horizontal velocity equals horizontal distance divided by time, that horizontal distance that the block travels after it leaves the table. It's going to be d over t, which will be d over square root of 2h over g. And we can simplify that to be d square root of g over 2h. So far, once you know what to do, parts A and B aren't that bad. If you're really stuck, a lot of times just write down everything you know. And maybe you'll see certain variables and certain equations you can use will jump out at you. These are the last two parts of this question. First, we want to determine the work done by the spring. Well, we know work equals force times distance, but it also equals our change in energy. So we want to know the work done by the spring on the block. So we need to look at the block's change in energy. We know it goes from a state of being at rest to having kinetic energy. So if that block has kinetic energy, that was given to it through work done by the spring. So we need to look at the change in kinetic energy of the block. We know delta means final minus initial. We know the block had no initial kinetic energy, so any work done by the spring is that final kinetic energy that the block has. So work done by the spring equals kinetic energy final of the block, which is going to be 1/2 times the mass of the block times its velocity squared, or its speed. We have that from part B, so we can write 1/2 times m times squaring this expression here will give us d squared g over 2h, and we can write that as md squared g over 4h. And last but not least, we want to determine the spring constant of the spring. In that case, we are going to use the conservation of energy. So the maximum elastic potential energy of the spring is going to equal the maximum kinetic energy of the block. These are both maximum values because now we're considering our system to be the spring, the block, nothing else. No earth in our system means we have no gravitational potential energy. But we could deal with that by setting the top of the tabletop to be 0 gravitational potential energy, but in this case it's just a little bit easier to just say our system is purely the block and the spring. So our maximum elastic potential energy is going to be 1/2 times our K times our maximum compression, which is X squared, and that equals our maximum kinetic energy, which we actually also happen to derive in part C of md squared g over 4h. Alright, now we just want to solve for K, so we could say that K equals, we can get rid of this 1/2 by multiplying by 2, then this 4 becomes a 2, so we can say that K equals md squared g divided by 2h x squared. And that's it for this problem. This is our final free response question for this video. So we have a block of mass m released from the top of a frictionless quarter circle. It then slides onto a horizontal plane where it comes to rest a distance x meters from the beginning of the horizontal plane, and that part has friction, obviously, because the block slows to a stop. And we're given the force of friction as F. So for part A, we want to determine the magnitude of acceleration as the block slides along the horizontal plane. Notice it says magnitude. We know the acceleration is in this direction, opposite our direction of motion, but the magnitude means it doesn't matter whether that acceleration is positive or negative. So give that a shot, and hopefully you realize we should be using Newton's second law because we're dealing with forces. And acceleration, we know, equals F over m. That actually is the correct expression because our F and our F for friction are the same variable. We're looking at magnitude, so you could take the absolute value of this and just write that A equals F over m. Now we want a formula for the radius of the incline. This one's a little bit trickier. Alright, well, we should notice that we need to use the conservation of energy here. You might be able to see that from our given variables. We know the block starts out with only potential energy, and that's gravitational. There's no elastic potential energy here. So that's UG. Let's set this to be our 0 UG. Once it reaches that 0 UG, all of its energy is now kinetic. You could add subscripts here to say we're talking about initial and final. Alright, our gravitational potential energy is going to be mg, this height here is r, that's the radius. You can determine that from our starting point, and that will equal 1/2 mv squared. Our m's cancel, and basically you can see that we're being allowed to use a variable that we don't need. That doesn't mean we're doing it wrong just because you don't use all the variables. So now we can say that r equals rv squared divided by 2g. So that will conclude this video.